sometime we would also like to see, the next question would be that how will we compile, how will we run, or how we will simulate. So what are these three different things? What does each of them mean? Compile means, because it's a high level language, so we need to compile it, we need a compiler, and after compilation the execution would be formed, executable would be formed, and that executable, once we will run, that run is also called simulation, because we are simulating the hardware behavior. So how do we compile, run and simulate the hardware model? Now, because the language is specific, the software which would compile, run and simulate are also are different and basically more specific to those languages. Now, there are multiple of these commercial tools which are there, which are usually there are couple of EDA companies, electronic design automation companies. They build, they design these software, and we can use these softwares to compile, run and simulate. So these big 3 or 4 EDA companies, Mentor Graphics has a Model C, which is quite popular Verilog compiler and Verilog simulation tool, and Cadence has Incisive, Synopsys has VCS, and Xilinx has Vivado. So we would be using Xilinx Vivado at some stage of time whenever you will come back in the campus. So because Vivado not only would be able to compile and simulate, but it would also be able to synthesize. So after using synthesis, you can burn that design onto FPGA boards. So once you are back, so then we can have these FPGA boards experiments. The other these commercial tools will have many more features, like it help you quite a lot in your debugging and visualization. On the other hand, there are free softwares which can be used for compilation and simulation. So in case of Verilog, iKeras is a popular one which can be used, and for GHDL is another one which is only for VHDL. There are some online platforms also like EDA Playground. So EDA Playground help you to write this Verilog code onto an online browser where you can compile, you can simulate all the online. Yes, I can always pause, no issues. So I'll come in 10 minutes if I will be almost.
Yeah,
okay. So now during this course we would be using free HDL simulators, iKeras most of the time, and so this iKeras software you can install onto your computers. I'll give a quick demo onto using my computer. So because we would be compiling it using a iKeras software, it's a command line tool. Now to view the waveform, we have to explicitly dump these waveforms and then see them in a waveform viewer. So to see or to dump the waveforms, we have to add additional initial module in our test bench. In the in that initial module, we'll write initial, begin, dump file and the name of the file, and then one particular command is sufficient, dump vars. So this dump vars, whatever variable it finds in your whole module test bench, it will dump all of them in that VCD file. VCD is value code dump. So this would be a dump file which can be used to see our waveforms. So now let us quickly look at the demonstration. So I'll give you two demonstrations, one based on EDA Playground and the second one based on in your own installation of iKeras. So let's say this code, I'm directly using the code which I have written, and let us see that in the browser. So let's have a quick understanding of this EDA Playground. You can see on one side you are writing your design. Design is being saved as design.sv because System Verilog. SV is the extension for System Verilog, because System Verilog is a superset of Verilog, so that's why by default EDA Playground take it like a .sv extension. And then we have written the same code here, and this code similarly testbench.sv is also written. So this is also the similar thing what we have written. You will see two initial modules. One initial modules have all the stimulus part, the other other initial module dumps the variables. So on the left pane you can see that whether your design is of Verilog, System Verilog or VHDL. So because we are using Verilog and System Verilog part, so there is no UVM, OVM, and there is no other libraries which are used. So here in tools and simulators you can see there are various commercial softwares and then also free simulators. So in free simulators we would be using the latest version of iKeras, and we cannot use this commercial software because all of them are paid and requires some license fees. So let us use the latest version of iKeras as the software, and then after doing all of these things, then we can also say that after running we would like to open in EP wave so that we can see the waveforms. So after all of these things are done, we can save it and we can run it. So after running you will see two things. One, that you will see a waveform viewer. In this waveform viewer you have four signals: RA, RB, W carry, W sum, A, B carry and sum. And you can see the input and output of all of them at point. You see that at exactly at 10 nanoseconds when we have changed our input, our output got changed immediately. So this is how what this is the meaning of our assigned statements, that it changed our output immediately. So similarly at any particular point of time, now we can check what is the input and corresponding to that input what is the output. So now we can close this, and if we close this, then we see that in the log or in the test in the prompt, you see that these variables have been displayed, or basically these print statements have been given: a equal to 0, b equal to 0, sum equal to 0, comma carry equal to 0. So all of these things are written in the same way, the way format we have defined. So this is how we can use EDA Playground. So you can sign up in this EDA Playground and you can use. The other alternative, you can install this iKeras onto your own computer and then can work. So let us see that part of demo as well. So I have created one directory here, and then I will start with the installation part. So during the installation, first thing I have to do is I have to get it from the GitHub. So the statement command is git clone git github steve iKeras iverilog.git. So after getting this git, then I see that one directory has been created, iverilog, and in this directory there are so many files. We have to see how do we start configuring. There is one particular sh file which is called autoconf.sh. So first we'll run this autoconf.sh, and after this we see again, then we see that there is another file which has been created, which is configure. Now we will run this configure file. So after running this configure, a make file would be generated. So if we see again, now a make file has been generated. So this make file we can use to make or to compile this whole software. It will take a couple of seconds. Yes, now we see it is done, and now we can install this iVerilog into our computer. So for installing, we can write make install. So when we say make install, it says error because permission is denied. So there are two alternative for this. Either we use, if we have a root permission onto our system, then we do sudo make install. Otherwise we define the directory where it need to be defined, it need to be installed, and that directory should have permissions. So after installing, now we can see that this has been installed, and now we can start using it. So if for using it, I have created I have again downloaded the same file which I have created the same file. So you see ha.v is the half adder module which defines the data flow model of our half adder, and we have in ha.testbench we have the test bench which provide the stimulus which instantiate the half adder, and it also dumps our VCD files. So now given this half adder files, so first thing we have to do is we have to compile them, and for compiling the command would be iVerilog. So iVerilog, then we list all the files which we need to compile, and after compilation step, then you see one a.out has been created. So this is the executable which has been created. If we run this executable, then all the execution has happened. So basically all the stimulus is given to our test bench. Stimulus which is generated in our test bench is given to our design under test module, and you see that at every time it says that at what are the values of sum and carry. So it looks correct because a equal to 0, b equal to 1, sum should be 1 and carry should be 0. So in the other similar way, so all the combinations are giving us correct result. So let us see the output along with that. So this output, whatever we are writing in $display, that would be given on the prompt, or basically would be generated here itself, along with, because we have also written dump vares and we have generated a VCD file. So this VCD file is here. So if we would like to see this VCD file, this is actually a text file, but we can see this text file only using some particular editor or some particular tools. So GTK Wave is a popular tool which can be used to see this VCD file. So let us see this VCD file using GTK Wave. If GTK Wave is not installed onto your system, first you have to install GTK Wave, and then you can use that to run or to see this particular waveforms. So GTK Wave has been started. In GTK Wave, I can see these are the 4 signals which are there in ha.tb, and I can use any of them. I can append them in my signal waveforms. So here I can see these signals that for initial 0 to 10 nanosecond, that all the values were 0, and after that, after 10 nanosecond, values has been changed, RA and RB has been changed, and so our output is also changed. On the other hand, if I want to see my signals inside ha.inst, that means that particular instance of half adder, then I can select those signals also and then append them in my signal viewer or GTK Wave viewer. So there also I can see the similar signals. So you can use this GTK Wave to view the waveforms, and you can use $display to print all the outputs. And this is how we will see how we can write in Verilog. So in summary, in today's module, what we have seen that how how we can write a very simple program like half header in Verilog. And the learning style, so because Verilog is going to be quite a quite a complete language, extensive language which has a lot of syntax. So what we will do is we will pick and choose small syntax like this. We have figured out a couple of these things today, and so we'll use these things and we'll create our modules using this. And we'll have similar demos or similar explanations whenever we introduce a new syntax in Verilog, and then we can practice it by creating our own modules, and that's how we would be learning a Verilog. So it would be learning by doing, rather than treating it like a language where we will first define, we learn all the syntax and then we apply. So rather than that, we would we'd see that in what application we can use that syntax, and then we will learn accordingly. Thank you very much.